I don't know. Let's check. Next time you go to your Canvas page, you can take a look at notes that we've done and completed by clicking on this downloadable link, and it should come up with a PDF. Now, I'm kind of using PowerPoints for this, and PowerPoints have certain ways to deliver their handouts. You can have it like 3 per page, or 6 per page, or 9 per page, or 2 per page, but you know, you sacrifice the resolution and the size. So I don't know how you guys want the notes. Is this okay? So anything that I might write, did I write anything on this? Oh, maybe I uploaded the wrong one. So if I write anything on these slides, they should pop up over here. So maybe I uploaded the wrong notes for you. But if you have this printed out on a piece of paper, you know, the 6 slides setup is going to be whatever it is. So if that's okay with you, then I'll keep doing the same thing. If you want to get a hold of this before class, do you know where to find it? No. Okay. So you would go to my math lab. I guess I should have gone in as a student, but I think it's the same idea. I could still go in as a student. You have 2 links. You have all assignments or course home. I think if you go to course home, it'll give you a bunch of links that you can navigate through in my math lab. You can see assignments. You can see the chapter content, which will give you the textbook. The interactive ebook is another version of the textbook. Study plan is if you want to practice. The grade books won't be really used that much. Tools for success would be some other things that you can take a look at. I haven't even looked at that. I think it might have something to do with technologies. Multimedia library is where, yeah, Jake? Oh, 1 and 1-2 are due on Sunday. I keep forgetting to put the due dates there, but let's just plan on those 2 homework assignments being due on Sunday. Okay, so the multimedia library would be the place to go. If you click on PowerPoints, and you could do all chapters, or you just want to do chapter 1, you can do a specific section, or you can find all the sections, but you'll see it here. So you can download it and print it out if you want, or you could just keep it on your computer and then annotate, whatever. But these are, for the near future at least, this is how I'm planning to deliver the class sessions. We are falling behind a little bit because these PowerPoints tend to be a little bit longer than I would like, but I think what we'll do to try to catch up once or twice this semester is I'll record a PowerPoint lecture online and ask you to view it before coming to class. I'll probably do a couple of those, and then in class we'll do some other kind of work that's not lecturing. Anybody know what that's called? That's what educators have been calling the flipped classroom, where you get the lectures outside of class, and in class you do some other kind of work. So anyways, that's how you can access your PowerPoints, or the PowerPoints that I'll be using. Also, I don't know if you noticed, but there's a video of the last class that we had, so you can access that as well if you need to try to remember something, or if you weren't here. I'll record videos, so I'll have notes for our class, and everything will be up there. Okay? Questions? All right, let's get to it. We are still talking about systems of linear equations and matrices, but this time we're going to jump into the idea of a vector equation and start using vectors. Now this is normally, well, I'll play that little segment from Despicable Me. Remember? Did you guys watch that show, that movie?
Size and direction.
Size and direction, magnitude and direction. So Victor changed his name to Vector because he's planning some evil plans with direction and magnitude. A vector is essentially something with a direction and magnitude. But I'm not going to play that. So let's just jump into the PowerPoint here that talks about vectors and vector equations. So a vector in R2, by the way, R2 is two-dimensional plane of ordered pairs. So this is just a set of real numbers. And they use, this is a funny letter. It's not a usual font in your Word document, but it's usually 2 bars for the R and then just the regular R part. So it's usually not like, this is an outline version of it, so this isn't really how it would look like when mathematicians write the set of real numbers. But R2 will be the set of all ordered pairs such that X and Y come from the set of real numbers. So basically, if you draw an XY plane, and it doesn't really have to be XY, but if you draw an XY plane, it's every single point on that plane would fall under R2. So now a vector, a matrix with only one column is called a column vector, or simply a vector. So in general, when we say vector, we're going to assume it's a column vector. Now we can also think about row vectors, because we can look at a row of something and call that a vector as well. But in most cases, when we deal with vectors, we're going to assume that it's a column vector. So a column vector is just a matrix with one column and however many rows. So in this case, in R2, we would have 2 rows and 1 column. So this is a 2-by-1 vector, or 2-by-1 matrix. Oh, we don't say R squared either. Right. I worked really hard in my pre-algebra class, and even algebra classes, or even calculus classes for that matter, where people are reading this expression as x2. I said, no, that's not x2. It's x to the second power, or x squared. Right? You drill that into people's heads. And then now when you see a superscript like that, you think squared, second power. But in this case, it's not the reals raised to the second power. It's R2. So that's what we say, R2. Yeah?
W is a vector, right?
W is a vector. Yeah, so there's a couple ways to write a vector out. I can see that they're trying to distinguish this as italics W versus a non-italics W. And normally it would be boldface W, which I don't know if they actually tried to boldface it, but it doesn't look like it's boldface. Yeah, so the other easy way to handwrite this when you're doing it by hand is to put an arrow on top. to make it clear that you're looking at a vector and not just a regular real number. And by the way, your vectors can exist in R2, but it can also exist in what we would call the complex plane. So instead of real numbers, you could have complex numbers. Where the complex number would be written as a plus bi, where I is the imaginary number. And then you can have a vector in the complex plane, a two-dimensional vector in the complex plane as well. So these are other examples of vectors, and they don't necessarily just have to be in R, the real numbers. It could be in complex numbers as well. Or some other set of, they call it a field, as long as it's over a field. Have you guys seen the C with a little bar on it, complex numbers? Have you seen R with a bar on it like this, like in real numbers?
A lot of that you can
Yeah, they did stuff like this in Calc 3. I forgot what they did in Calc 3. Yeah, I know. Last semester, right? Just to throw more symbols at you, Q is the set of rational numbers. I know Q doesn't start with an R, or rationals doesn't start with a Q. But they use Q for quotient because rational numbers are fractions, essentially. And then there's the set of integers, which is Z. And all these sets of numbers are essentially the letter with a little, an extra slash to it or something. So I don't know why they call it Z. Anybody speak German?
I think it's from the German word.
Yeah. So the German word for integer apparently starts with a Z. Maybe it's called Zinteger. I don't know. No, that's not true. I'm just making it up. All right. So that's why we're taking too long, as I don't rush through these slides. R stands for the set of real numbers, appears in entries of the vectors. So the exponent 2 indicates the number of entries that you have. A number of, what did they call it in Calc 3? Wasn't that long ago. Components. It's the number of components that you have. So ordered pair, there's 2 components. And then for 3-dimensional vectors, it's triple, ordered triple. Elements in set theory. And since we're dealing with matrices, you can also call them elements here as well. Since we're talking about a column matrix, as a column vector, then you can look at it as entries as well. 2 vectors are equal if and only if their corresponding entries are equal. That's just the definition of equality. And 2 vectors, the sum of the 2 vectors is obtained by adding their components, their appropriate components. So I don't know if we need examples for these things. I can certainly provide some simple examples. 1, 2 is equal to 1, 2. And 1, 2 is not equal to 1, 3. You know, should I do more? So U plus V, if you have the vector U. So think about it should be boldface or arrow on top, but think about these things in the notes as vectors if they're not italicized. So here it looks like they're boldface here too. So they just forgot to boldface that. So vectors U plus V. If you were to add those 2 vectors, you would just add component by component. There's nothing, you don't mix any of them up or anything like that. You literally just add the components with the components. Okay. Scalar multiple. Now the word scalar comes from scaling, and that is going to be a real number being multiplied in front of a vector. So having a real number multiplied in front of a vector is now an operation that requires 2 different things, 2 different entities: a scalar number, a real number, and a vector. And so this scalar over here, this real number, is called a scalar because it scales the vector that you're looking at. Now, it either extends it or compresses it, depending if it's bigger than or less than 1. And you multiply each of your entries in your matrix by that scalar. Okay? So if it's not a vector, chances are it's going to be a scalar. Or if it's like a rectangle, then it's a matrix. Real number is called a scalar. That's what it says. I'm going to look at that later and say, what? So here's just a bunch of examples. There's also a combination of things where you can add scalar multiples of things. So you could do a simple scalar. Here are a couple of examples of just multiplying the vector 1, -2 by 4 or by -3. And then here's one where you have two vectors where you multiply the vector by a scalar and then you add them together. So this is your third example. And that's pretty straightforward, right? And if you guys were in Calc 3, then all this stuff is pretty review. A rectangular coordinate system in the plane. Each point in the plane is determined by an ordered pair of numbers. We can identify the geometric point with a column vector. You may also regard R2 as a set of points on the plane. So we can think about this as a point or a vector, and geometrically we can make a distinction between the point, AB, and a vector. And it's probably going to be coming up in the next slide, but we can think about the vector as a line segment from the origin to the point that it's pointing at. So mathematically, you can think about these two things as being indistinguishable, being the same thing. But sometimes geometrically, you might want to consider this ordered pair as a point. Sometimes you might want to consider this ordered pair as a vector. It didn't really make much sense for us to, quote, add points. But now if we're dealing with vectors, it kind of makes a little bit more sense for us to add vectors. But mathematically, you're doing the same thing. You're adding component by component. So here they're making a distinction between a point and a vector, but also saying that although you can distinguish these two things geometrically as different, you can also think of them as the same thing because they carry the same information. They carry A for the first component, B for the second component, and one is just written as a horizontal ordered pair with parentheses. The other one is written vertically with brackets. All right. The parallelogram for addition. So if U and V are vectors represented as points on the plane, then U plus V, the sum, can be considered as the diagonal of a parallelogram spanned by U and V. So U and V would be these 2 points, and again, you can look at those points as vectors from the origin. So U plus V would be taking the vector U and then taking the vector V and then putting it at the tip of U. So this vector V is the same as this vector V over here. It's just been displaced a little bit. And when you have a displaced vector like this, then you can follow where it ends up. And wherever it ends up is going to be the sum of the 2 vectors. So U plus V u plus v is going to be this thing. And that, by the way, is the diagonal of those two vectors. Have you guys seen all this? Should I just skip through this and...
Well, let us know what's important to you.
Well, I think the geometry of this is important, but you need to be able to do the calculations. Then go, continue. Okay. I'm just afraid I'm seeing a lot of sleepy eyes here.
Well, you'll catch them on the quiz.
Maybe we should have a quiz. When's our next class? Monday?
Don't make it seem like it was my idea.
No, it wasn't. I had it planned all along.
Yeah.
I had the quiz written already anyways. Okay, vectors in R3, just three-dimensional. And geometrically, we can look at a vector in R3 coming from a three-dimensional vector space, x, y, z, if you're familiar with that, as the ordered point, ordered triple, the point A, B, C, wherever A is, wherever B is, wherever C is. So the first component would be the x value, the second component would be the y value, and the third component would be the z value. So you can imagine something happening in 3 dimensions here, where you walk through this and then you get that point A, B, C. And if you draw a line from the origin to that point, then you have the vector, a 3-dimensional vector, in R3. So we can think about that as a point or a vector, again, carrying the same information where those 3 constants are involved. Now, we don't have to stop at 3 dimensions. We can go 4 dimensions, 5 dimensions, etc. And so there's an idea of an n-dimensional vector, or something that would live in Rn, that might have some information that might be important to us. So in that case, you have a vector in Rn. Anybody think? So geometrically, anything beyond 3 dimensions is difficult or impossible to visualize. But can we think about an application where it might make sense for us to use a vector in Rn? That's a lame example. Forces. Actually, Caesar's example is the example that I always use in my Calc 3 class. So that's why he said it. Grades. Let's use that one. Your grade is made out of, do you remember? Did you guys read the syllabus? Homework, exams. I distinguish the final different from the exams. You guys have quizzes? There's no extra credit. STEM speaker? Is that it? Oh, let's just say that's it. So your grades would really be a set of numbers, and there's a way to calculate your overall grade based on your homework performance, your exam performance, your final exam, your quizzes, and the number of STEM speaker series that you went to. So this holds 1, 2, 3, 4, 5 pieces of information. You have 5 pieces of information. You can just drop it into a vector like this and then do calculations as you need to. Now, it wouldn't make too much sense for me to add these 2 vectors. If I have Brian's vector and Caesar's vector, and if I add them, I'm just going to get another vector, but it's meaningless with respect to their grades, their scores. But I could do something else where, if I remember correctly, I don't remember correctly, but the homework was worth 10% of your grade? I don't know. Let's just make it up. 10%. The exams were worth like 25%. The final exam was worth 50%. The quizzes were worth, what's left? 10%. And then the STEM speaker series was worth 5%. So if I have another vector that tells me the percentage of contribution for each of these, each of your scores, each of these categories for your final grade, then I can do what's called a dot product. And I think it'll be called a little bit differently here. It'll be some matrix multiplication business that we'll do. But in Calc 3, when we're talking about vectors, we did this thing called a dot product, where I can dot your information with a special key that tells me how to distribute your grade. And then I'm going to get a value here that will end up being your overall final grade. Okay, so vectors are not necessarily restricted to just 2 or 3 dimensions, not restricted to something that we can visualize. We can go abstractly into more categories as long as we need information about different categories. All right, algebraic properties of vectors in Rn, or Rn in general. The vector whose entries are all zeros is called a zero vector. And what I want to do is I want to distinguish a zero vector versus a zero scalar. A zero scalar is the number 0. A zero vector is a vector with zeros in it. So because there is a distinction between a scalar and a vector, there should be a distinction between a zero vector and a zero scalar. And I like to make a big deal out of it because it's important that when you do an operation, you know whether to expect a scalar or a vector. And if you get 0, you might just say, oh, it's 0. But you should know if it's a zero vector or a zero scalar. So there's a few other vector properties over here. The vectors are commutative. They're able to switch. The vectors are associative. Commutative and associative in addition. When you add them, you can change the order or you can group them in different orders and you would still get the same result. There's a zero vector that's like the additive identity, which means if you add a vector to 0, and this is a zero vector, these are all vectors, then you would get the original vector. There's additive inverse, and the inverse is really just putting a minus sign in front. And if you look at this, if you look at this without the arrows, I mean, they don't have arrows, but if you look at this as if they were scalars, it seems like it all makes sense, right? Same properties as scalars. The difference is that when you start doing multiplication, they don't have the same multiplication properties because we haven't really talked about defining a multiplication for vectors. We can do scalar multiplication where you have a scalar times a vector, but we haven't done a vector times a vector. In fact, there's 2 different types of vector multiplication that we can look at. That's multiplication with 2 vectors. One of them is called a dot product. The other one's called a cross product, if you're familiar with that. And they don't have the same properties as we do in addition. Or they don't have the same properties that we do in regular scalar R properties in R. So the scalar multiplication properties here is like a distributed property. You can have a scalar multiplied by the sum of 2 vectors, and that can distribute to each of those 2 vectors. And then you can do that where you have 2 scalars that you're adding, and then times a vector. And I guess for these ones, it's important to really put the arrows where it belongs because you have to tell the difference between which one's a scalar and which one's not a scalar. So C and D are scalars in this case. and U's and V's are vectors. All right? So, again, obvious or seemingly obvious properties that might come in handy when we're working things out later on in the future. Some more properties. This time you're multiplying two scalars and a vector. This should be, again, the U is a vector. The C and D should be italicized here to represent that they're scalars. Looks like some stuff was happening when they were doing the formatting. And a scalar multiple of 1 doesn't change the vector. Okay. So these are your properties. Try not to take the ones, the multiplication ones, try not to take it for granted, because the addition one looks really, really familiar from our properties for real numbers. But when it comes to multiplication of vectors, it's a little bit different. So just be careful about these last few properties. Now, the linear combination part comes in this next bullet point. So if you have a set of vectors, V1 through Vp, there's P vectors here, and each of these vectors are n-dimensional vectors. And then you have scalars, C1 through Cp. You can define another vector, we're calling it y, as a linear combination of the vectors v1 through vp. Okay? So the idea of a linear combination would be very, very, very important for us.
It's like what you set up with the dot product and matrix multiplication for an example.
It's an example of what?
It can relate to the grades example.
Oh, the grades example. Yeah. Yeah, so the grades example that I have is kind of like a dot product, but it's not, that's not an example of a linear combination. Because a linear combination is a little bit different. So how is it different? So if we take an actual real live example, we could take a look at a couple of vectors here. 1, 2, and 3, 4. We can do one more. 5, 6. Oh, that's pretty boring. And then we could take a couple of scalars, same number of scalars, like -2, 0, and 7. So this is like your V1, V2, V3. This is like your C1, C2, C3. So we can define a new vector. Let's call it x equals. So a linear combination of these three vectors would be just a scalar times the first vector plus the scalar times the second vector plus a scalar times the third vector, 5, 6. Run out of room. So anyways, if you work this out, you're going to get your x is equal to a vector. And that vector, you can say that that vector is a linear combination of these three vectors. That's all they're saying. Now, the value in the linear combination idea is something that we'll see a little bit later on. But for now, just the idea of linear combination is important. So you can't square this or do anything weird to it.
It's just the order presented, which lets you know how they match. The C1 has to correspond with D1.
Yeah.
Like how's that supposed to go?
That's I don't know if that's that important.
Okay.
Yeah. I think the point is that if you have a set of vectors, when you say linear combination, all that means is that I can scalar multiply each of those vectors and add them all together. And then that's a linear combination. Now, the thing to look forward to in the future is that you might have a vector, and you might wonder, is this vector a linear combination of these three other vectors that I have? And then your task would be, well, to try to find those coefficients that would make it a linear combination of those three vectors. All right? So that's the idea of a linear combination. Here's another example that they have. Let A1, A2, and B be equal to this, and determine whether B can be written as a linear combination of A and B. So that's your general problem that you would be asking yourself. I don't like the fact that they're using X here. So the idea is that, can you find two numbers, two scalars? These are just regular scalar numbers. Can you find two numbers so that if I scalar multiply A1 by this number and I scalar multiply A2 by this number, that I can actually find this vector? So let's think about that. Can I multiply this by some number and multiply this by some number so that my result is equal to this? Let's throw out some guesses. Any guesses? 2 and 3, would that work? So 2 times 1 is 2. This is 6. That's 8. So that.
There's going to need to be any multiple 8
to 4 here. Let's you switch them.
That's true, then any multiple of A1 needs to be odd.
So would this work?
Yeah, that works.
So this is negative 6 plus 10, 4. This is negative 15 plus 12 negative. So it works? Yeah, so 3, 2 would work.
Check that no such number.
Well, if you keep doing this an infinite number of times, then you'll eventually say. But obviously, you don't want to do it an infinite number of times. So the way to do that is, it's essentially, I don't know if you guys look at this and say, hey, that kind of might look like a matrix, or maybe we can make it look like, it might seem like it's a system of linear equations. So generally, you're going to look at a problem like this and maybe create a system of linear equations and see if you can find solutions to it. So I'm not going to, but see if you guys can find another solution to this, right? And if you can, then maybe there's an infinite number of solutions. Because remember, our possibilities is that it has no solutions, it has exactly one solution, or the other case is that it has an infinite number of solutions. So we found one solution. Now, if you can find another one, then you're pretty much guaranteed that there's an infinite number. Okay? So here's how they decide to do it. And what they did was they scalar multiply the vectors together. So remember x1 and x2 are scalars. They're numbers that you're looking for, and you're trying to solve for x1 and x2. So you set it up like this, and then you scalar multiply the scalars, and then now you're going to have essentially 3 equations. How many unknowns were you looking for again? So 3 equations and 2 unknowns is essentially what you're going to have. And what you'll end up having is you'll end up having these three equations, and you can write them as a system of linear equations. Right? Now, once you write them as a system of linear equations, you can then go back and make it into a matrix. Remember the matrix of coefficients? If you have a system of linear equations, you can create a matrix of coefficients. Augmented matrix of coefficients with a 7, 4, negative 3.
So the C's were the augmented part?
So the B. The B was the augmented part. So you have the B vector over here. Now, these, your columns for your matrix, I don't know if you guys would notice, but if you look at vector A1 and vector A2, look at it for a minute. Okay? Now, when you have your system of linear equations and you extract the coefficient matrix, these are the same two vectors, right? And this is your B vector. So maybe we can skip that other couple of slides for next time you're doing this. You can just go from the vectors straight into the matrix, the augmented matrix. So now the augmented matrix, you would do some sort of row reduction, elementary row operations to get it into row echelon, or more like they went to reduced row echelon form. Right? This is reduced because the leading entries are all 1, and then the columns within those pivot columns are all zeros. So you have a pivot column here in the first column and a pivot column in the second column, and this is the augmented part, so there's nothing else that exists. So the last row will represent the equation 0 is equal to 0. So the fact that this is 0 is equal to 0 instead of 0 is equal to a number that's non-zero means that we have at least one solution. And it looks like, do we have any free variables? We don't have any free variables here, right? So because we don't have any free variables, we're not going to have an infinite number of solutions. So now we have that one solution that we found turns out to be the only solution for the system. So the solution is x is equal to 3, x1 is equal to 3, and x2 is equal to 2. So we can write B as a linear combination. This is B as a linear combination of A1 and A2. Had you found more solutions, like an infinite number of solutions, you can still say that this is a linear combination, and you can choose whatever pair of numbers that you found for x1 and x2. Questions? All right. Yeah. Yeah, I think that would make things a lot easier. So remember the original problem, you can just drop those vectors into column vectors in your matrix, and then the augmented part, and then do the row reducing.
Are the tildes in between a standard notation?
I don't usually use tildes, but they say it's equivalent. The tilde is like a universal sign of saying equivalent. Well, actually, it's more like approximately.
What do you use?
I use an arrow, a longer arrow, so I can write exactly what I'm doing. So I would have multiplied row 1 by 2 and added it to row 2, and then replaced row 2. But that takes a lot of work. And then this thing took 2 steps. They took 2 steps here, actually. They also took care of row 3. Row 1 multiplied by 5, added to row 3, and replaced row 3. So that little tilde sign, I would have put this arrow if I was showing all my work. Yeah?
So
I think it would be good, because if you got the wrong answer and I'm checking your work and I don't see any work, I just see these little tildes, then I don't know how much credit to give you because I didn't know the steps that you took. But if you took these steps, I know where you made a little mistake, and if it's a little mistake, well, that's 1 point off. If it's a bigger mistake, then it's more points off. But if the whole thing was wrong and you didn't show any work, then that's all the points off. All right. Questions? Linear combinations. You can write a vector as a linear combination of 2 or 3 or many other vectors. And so here they rewrite the matrix as a matrix of vectors. So those vectors A1, A2, and B that we saw in the beginning of the problem over here, you can just write them as A1, A2, and B in a square bracket set up like this, and then they would understand, or people would read this and understand, oh, these are vectors. So they would have columns, so this would actually be a matrix, however many elements you have in your vector by 3. This is a 3 by 3 matrix, it'll turn out. Because A1, A2, and B are 3-dimensional vectors. And then there's 3 slots, so that's the number of columns. So it's a 3 by 3 matrix. Okay? And MATLAB is nice like that too. If you define column vectors and then you write your vector like this, it's going to know that to transform it into a matrix. Now, it'll give you a problem if A1 and A2 are 3-dimensional vectors and B was a 4-dimensional vector. It's not going to like that. It's going to give you an error because it has to be all the same size. I don't know if MATLAB would know how to do that. Would automatically put a 0 there. It wouldn't. The dimensions wouldn't match up, so it might actually give you an error. I'll have to check. Okay, so the vector equation x1 times a1, x2 times a2, all that stuff is b, has the same solution set as a linear system whose augmented matrix is this. So remember, when you have a system of linear equations and you put it into a matrix, you kind of ignore the variables that you're solving for, that you're looking for. So you got x1, x2, all the way to xn, and you kind of ignore that. But in the end, that's really what you're looking for. You're looking for values for x1, x2, all the way to xn. But what's important? What's important is that the coefficient matrix, and the coefficient matrix will just easily come from those vectors. And you take those vectors and you put them as columns for your matrix and augment it with B, and then now you have the matrix operations to help you find the solution. So B can be generated by a linear combination of A and B if, or A1 through AN, if and only if there exists a solution to the linear system. So what they're saying is that these two things carry the same information. So if you find a solution for this augmented matrix, then you find a solution for your original problem. Okay. More definitions. Span, the span. If V1 through VP are vectors in Rn, then the set of all linear combinations is called the span. And then they use span, curly brackets, and then they list the vectors. And this is called the subset of Rn spanned by the vectors v1 through vp. So the span is essentially the set of vectors, or points, but the set of vectors that is a linear combination of those things. So the simplest example of this is in R2, when you have one vector. We can go to R3 to make it a little bit more interesting, but let's start with a simple example. And we'll start with a simple example in R2. And we'll just use one vector. So let's call this V1. What's the span of V1? So span of V1, there's only one vector here, so it's a linear combination of this vector. Can you imagine what that looks like?
What are you combining
With itself?
vector with vector?
Well, this is the only vector that we have.
So it's just what it is?
A little bit more than what it is. Itself? You think it's just itself? What? What? One times itself? No. You made him say it. What is it? It's close. I mean, you guys are there.
That vector plus 0?
No.
That
So
vector times that vector?
that vector? No. What is it? What's the multiplication part? You're multiplying by what?
C1.
C1, right? And what's C1?
C1.
We don't know, but it's not just 1. It could be 2. It could be 0.
Okay.
It could be 5. It could be -3. Right? C1 can be anything.
When we define B1, are we going to define C1?
Well, the span doesn't define C1. The span says that you can write this as a linear combination. So I guess this is, there's an infinite number of them, yeah. No, not plus. You went a little bit farther than what you should have. So the span of V1 would be C1 times V1, where C1 can be any number. And somebody said infinite number. So infinite number of numbers here, or infinite number of vectors, where C1 can be anything, right? That's the definition of a span. It can be written for where C1 through CP. In this case, we only have one thing. And we have nothing to add, so there's nothing to add. So C1 can be anything. So give me some examples of vectors. Vectors in the span. I guess this is a more difficult example than I expected. So some examples of vectors in the span. I could tell you that 1, 2 is in there because you guys were saying, well, 1 times C1. That's in there, yes, but there's more vectors in there. 2, 4 is in there. 0, 0 is in there. One more. -1, -2 is in there. So there's infinitely many of them. By all you have to do is change the value of C1, right? So the span is really all these vectors. If you look at them as points, can you imagine what this might look like? What? Straight line. A little bit more, straight line, passing through the origin, 0, 0. Slope of 2. Yeah, I don't know. That part I don't care about. But you can, yeah. So you could picture this, right, in your head. You draw a 1, 2, you draw 0, 0, draw a line passing through there, and that's a line. So a span of this vector happens to be a line. Now let's stay in R2 and let's add another vector. What's another vector we can add? 3, 4. I was wondering if anybody would add 2, 4 to this. Let's add 3, 4. Now what's the span of this? So the span would be C1 V1 plus C2 V2.
So, when we see curly brackets, we think span.
You think sets in general. So the curly brackets here has to be preceded by the word span to actually be a span. But if you see curly brackets in general, you just think of that as a set, and then each of the elements in the set. So this is essentially saying this is a span of the set of these vectors. So I have this, and you can probably throw me some examples of vectors that would live in this span, right? Does 1, 2 live in this span? If C1 was equal to 1 and C2 was equal to 0, right? Does 2, 3, or 3, 4 live in this span? Yeah. So those are 2 easy ones. Oh, what if we add them? What if C1 and C2 are both equal to 1? Would 4, 6 live in the span? Yeah, because I just told you that C1 is equal to 1 and C2 is equal to 1. What? 8, 12? Yeah. Okay, so now the question is, oh, there's a lot of numbers that there's a lot of vectors I can choose for this, right? Can I choose any ordered pair? I wonder. Can I choose, is 100 100 in this span? There's no restrictions. I probably made this a little more difficult than what it should have been, but can you find C1 and C2 so that you get 100, 100?
I don't know. That's what we were doing.
Yeah, that's what we're doing. So the,
I don't think we get 100, 100 though.
you don't think we can get 100, 100?
Well, can we get 1, 1?
Oh, why don't we do that? Let's try that instead of 100, 100. Can we get 1, 1?
I didn't see it.
Yeah? Okay. Let's just say yes. We're not doing any work.
Well, okay, so C1 and C2, one's positive half and the other one's negative half. Right.
All right, here, why don't you guys take out a piece of paper and do it real quick?
Yeah.
Yeah, how about that? That was a swell idea.
So you're saying C1 is the positive or negative half?
No, you work it out. So you have those vectors, treat those vectors like column vectors of your augmented matrix, and then you have your augmented part is the result, which is 1, 1, right? So see what you get. did it already? Okay, well, hold your horses. Let everybody else figure it out. What was it again?
Negative half and positive half.
Negative 1 half will be 1, 1 half will be 2.
Okay. So, if you guys do the full-on reduced row echelon form, maybe you got something like this, and I'll put this little squiggly over here. So you guys got negative 1/2 for the first one and positive 1/2 for the second one? So in that case, we've found that 1, 1 is in the span. I randomly chose 1, 1, but we could have chosen any other value. And if it's in the span, then does any point that we make up in all of R2 in the span?
Because you can multiply with 1 and then again multiply by any numbers, like 100 and 100. So this one you can get 100 and 100 as well.
So looks like we can, huh? Yeah?
Maybe I'm really bad at this, but I'm getting 1/3, 1/2.
1/3, 1/2?
We got 131 and 241. We multiply row 1 by what, -2?
Uh-huh.
Add it to row 3, and you end up with 0, -2, -1 for row 2.
0, multiply this by -2, so -2, -2,
-1.
-1.
And then you're going to multiply that row 2 by -1/2,
Uh-huh.
and you'll get 0, 1, 1/2.
Yeah.
But you still have 131 as row 1.
So you need to multiply this by -3,
Uh-huh.
and so that would make that disappear. This times -3 is -3/2 plus 1.
I'm really bad.
Practice. Just practice. All right. So in any case, this happens to be, we could probably find a way to show it at a different time, but the span of these two vectors in R2 would end up being all of R2, which means if I pick any random point in R2, you can find me the coefficients of C1 and C2. Graphically, it'll look like this. No. Let me not be a smartass. 1, 2, 3, 4. What this would look like. Ah, come on. What this would look like would be a graph paper. With the lines going parallel to those arrows. That's what it would look like. Because if you imagine the graph paper, right, and then we say the point 1, comma 2, and then you move 1 unit to the x and then 2 units up to the y. Instead of saying 1, comma 2, we can say 1/2, comma -1/2, and then you're scaling each of those vectors. All right? So think about this. This is not an obvious idea, but if you can think about the graph paper that you would get from the 2 vectors that would fill up the whole space, then that's how you can find your span. Yeah?
Not any two vectors, if they're parallel, if they're two vectors that are like scaled versions of each other, it will just be a line.
If the 2 vectors are the same vector or collinear,
Yeah, collinear.
if the 2 vectors
Then you just get a line.
are scalar multiples, then imagine adding one to the other. All you're doing is stretching along the same line. I don't know what's going on with my computer. I think it's tired. All right, so here's another visual of the span using R2 or R3. If you have 2 vectors, or the span of one vector in R3 would be a line. And think about that as just the span of one vector is just a scalar multiple of that vector. If you have 2 vectors, wants to be done. If you have 2 vectors, no, now it quit. It really wants to be done. Come on, last one. If you have 2 vectors in 3 dimensions, then the 2 vectors will span a plane. Okay? If you have 2 vectors in 2 dimensions, those 2 vectors span the plane, but the plane is the whole thing in R2. If you're in 3 dimensions, spanning a plane is not the whole R3. It's just a 2-dimensional vector.
You need a third vector.
If you have a 3rd vector in R3, then it could span the whole space. Okay? So a linear combination would be a line or a plane or a 3-dimensional space if there's 3 of them. But those lines, those vectors, have to not be parallel, not have to be the same or a scalar multiple of each other. Okay? So the easiest thing to look at is in R2 with 2 vectors. And if you look at the 2 vector example that we did, try to imagine, this is frustrating now. So try to imagine what would happen in R2 if you have 2 vectors, and draw those vectors and draw parallel lines that would match up with those vectors, and imagine how the scalar multiples would look like. If you could do that, then you would have a good grasp of a linear combination. And if you can't, just try to read through it. All right, my computer's done. Oh, Siri actually said what I said too. It's looking for 2 vectors, well, span, plane, okay. If you have 2 batteries in 2 dimensions, whatever. All right, you guys will have a quiz on row reducing matrices on Monday.
So,
Monday, right? Today's Wednesday? So next Monday, on Monday. Next class.
so I'm still a bit unsure on